Yeah, comes on everyone. Let's start off. Great. The last thing that we did was the post office box. So we are still left with a little part of current. We'll finish off that and start with ray optics. Others do keep your cams on. And the last thing we also saw about potentiometer. The next thing, this is important. It does come a lot in mains. Again, don't worry about writing the notes. You will get the PDF. So focus on listening, understanding, and solving the questions. Yeah. Great. You got something. You can always type in the chat box or you can unmute and ask me if you have any doubts. So this is called half deflection method. So this is an experiment to find the resistance of a galvanometer. So till now, if you see all the experiments that we did, right? Ammeter was measuring current, voltmeter was measuring voltage, meter bridge was measuring resistance, potentiometer was measuring unknown EMF and the unknown internal resistance. Right? The post office box is same as meter bridge, but instead of a wire, you have that plugs. The half deflection method is to measure the distance of the galvanometer. So what is the experimental setup? So first thing, you take a resistance with a galvanometer. So this is some R. This is the galvanometric resistance G. And let's say you have a battery. And let the current be I. So we get I is equal to V by R plus G. Then what you do, you take a shunt resistor. Galvanometer, remember the meaning of a shunt resistor? Keeping in parallel. So you take a resistance and keep it in parallel. The shunt resistance ka value is S. This is still R and this is still G. You connect the same battery. And now what you do, so basically here G is the resistance of galvanometer. H is the shunt resistance. So now what you do in this experiment, right? We have to keep adjusting the shunt resistance. Normally they keep a rheostat so that you can adjust the value. Adjust the value of S till the reading in the galvanometer becomes I by 2. So now we will get a current here. This will be some new current, I dash. And here this current will be IG. It will split. Till the current in the galvanometer IG becomes capital I by 2, where capital I was this current. So this is the half of the previous current. That's why it's called an half deflection method. You're getting the experimental setup. So when you put a shunt resistance, the resistance in the circuit will change. And now the current also will split between the shunt resistance and the galvanometer. Now, if you see, right, visually it is more easy for you to figure out, isn't it? Initially, let's say the galvanometer was deflecting some 30 degrees. Now you keep changing the value of S till the deflection is some 15 degrees. And what is the current here? So here the current will be I dash will be V by total resistance, which is R plus GS by G plus S. That's your equivalent resistance. And what is IG? So the current IG, right? It will divide in the ratio of opposite resistance. So it will be S by G plus S into capital I dash. So substitute the values here. So we end up with, let me do it in the next page. I can finish off here only. S by G plus S, and I dash would be V by R into G plus R into S plus G into S by G plus S. Yeah, so that G plus S and G plus S will cancel, but IG is I by 2, which is V by 2 times of R plus G, which is V into S by RG, RS plus GS. We will cancel, it will go that side. This would be RG plus RS plus GS. Remember the derivation, it's important. You will see why. Because tomorrow in advance, right, they'll ask you a question like this: 1/3 of a deflection. Instead of an half deflection, they'll say 1/3 deflection galvanometer. They can change the experiment, right? So instead of IG will be I by 2, you will take I by 3 and you'll still solve the same thing. So when you do this, one RS will cancel, one GS will cancel. You are stuck with, you want to find G. G will be RS by R minus G. There. Quite an important result. Where R was the resistance initially, which was in series, and S is the shunt resistance. So how you do the experiment? You keep the galvanometer in parallel in series to a resistance R. Find the current. How do you find the current? You see the deflection in the galvanometer. It will have some reading. Let's say it is showing 4 amperes. Then what you do, you take a shunt resistance, means taking a resistance in parallel and keep it in parallel to the galvanometer. Because of this, two things happen. One, the whole resistance will change. Because of that, the current in the circuit itself will change. Initially it was I, now it was I dash. Second thing, this I dash won't flow through the galvanometer, it will split. Only some of it will go in the galvanometer. Now this experiment says you have to adjust the value of S till the current becomes off. That's the whole premises of the experiment, and that's why we call it an half deflection galvanometer. If they say 1/3 of a deflection, then it'll put 1 by 3. 1/4 deflection, 1 by 4, and so on. You solve it, you get this thing. Now the headache is this. In the exam, the question would be like this, and it has been asked multiple times in mains and bits. And people have no idea what to do. They'll simply say like this. In half deflection method, they'll start the question only like this. There, here only fuse will blow off. Like people will think like, what the hell? What is half deflection method? They will say the resistance is 10 ohms. The shunt resistance is 2 ohms. Find the resistance of the galvanometer. We just G there. Done ho gaya. This was a question. Most people don't know what is half deflection galvanometer method. Even if you know the method, then you have to go and derive the whole thing. It would eat away time in your, the exam. So the formula is G is equal to RS by R minus S. So yeah, I would strongly recommend you remember this. So this will be 10 into 2 by 10 minus 2. That's 20 by 8. 10 by 4, 2.5 ohms. Very important mains ka question. This is a mains and bits ka concept. So there, that is the thing. So half deflection method. In advanced perspective, they will change the whole experiment. They will say it is 1/3 deflection or 1/5 deflection. That itself will be a new thing. Yeah, and the main precaution, the resistance R, you have to make sure this guy is greater than G, or else this experiment won't work. Or else the denominator will become infinity, undefined. So all clear with this? This is there for mains. It has come a lot of times, and your seniors, they have goofed up also multiple times. Main thing, the word, right? The half deflection method, that itself will make you feel like what? So keep this in mind. So technically with this, we are done with current. But there is one more part which is removed in the mains portion, but it is still there for your CET and still there for your bits. So we're just going to do it, not a big deal thing with this, but small things. Color coding. If you have ever seen a resistor, this is how they would look. If you ever seen a resistor, this is how they look. Look at the colors here. So these things this is called color coding. So looking at the color, you can tell the value of the resistance. There have been a lot of questions on this, but they removed it 2 years back in mains. So technically they should not ask it, but CET mein to hai, bits mein to hai. So yeah. So what is the idea here? It's pretty straightforward. You can see this thing is called, a 3-band resistor, 4-band resistor, you can call this. So here, look at this thing. How many colors are there? 1, 2, 3, 4. So this is called a 4-band resistor. If you have 5 colors, we call it 5-band resistor. So what is the meaning of this? The first color, which is starting from left, is the first digit. The second color is the second digit. Third is the third digit. And this last one is called tolerance. Now, how do you know which is left and which is right? The ending color will be always either gold, silver. Normally, those are the colors that you will always have. That is how you know which is the last digit. So look at the resistor here. There is a gold color here. So you're supposed to read from this side, brown, black, red. That is how you read. So the gold or the silver will be always the last. So how to read this? Look at the numbers here. So black means 0, brown means 1, red means 2, and so on. So let's just take this example. So let's say I have colors like this. I have red, then let's say I have green, then let's say I have blue, and then let's say I have some golden color. These are the 4 bands. Red means 2, green is 5, blue is 6. So this is how we read. So the first digit is 2, second digit is 5 into 10 power 6. So that will be your third digit. So 2 is your first digit, 5 is your second digit. The third one is the power of the 10. So this is the power of 10. That means this resistor ka value is 25 into 10 power 6 ohm. The last thing is gold. Gold means you can see this is basically the error, the tolerance. So this thing is plus or minus 5%. So this thing has an error of 5%. If it is silver color, error is 10%. Clear this? Now the headache is how will you remember the colors? If you are in the CBC or CET, right? They have mnemonics. School may must have done this kind of things. There is some stupid mnemonic like this. Say, B.B. Roy, Great British, is a very good wife. So I don't know what the hell is that. There is some way to remember this. So the first color B is black, blue, red, orange, yellow, green. I think this is brown, violet, gray, white. So that is how, yeah. You figure out how you want to remember this. This is one mnemonic they have. So anyways, now can you see this one here? Can you tell me what is this resistance here? The one in the picture, can you tell me what resistance is that? What is the first color? Brown. Brown is 1. Second color is black, which is 0. Third color is red, that is 10 square. Last is brown, so 10 power 5%. So that is 1, 0 into 10 square plus or minus 5%. 1000 ohms. Clear with this? So they'll give you this picture and they'll ask you find the resistance. Or they could ask you something like this. This was actually PYQ. They gave you this and they ask you what is the color coding, reverse. This thing, right? Even if you don't know the exact color ka numbers, you can still get this if you're smart enough. You should have an idea what is color coding. It is okay if you don't remember which color is which number, you can still solve this. This is a 5-band resistor. So there are 5 colors basically. Look at the numbers, huh? 333. So that is basically 333 into 10 power 3. Did you notice something? That means all are threes. So that means I don't know what is the color, but all should be same color. This is orange, orange, red, orange. This is gone. Orange, 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 orange. That can be right. Orange, 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 red. That is gone. Orange, 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 orange. So answer is either 2 or 4. Making sense? Because all are 3. The color should be same. Now the thing is, you should know that 5% is gold. So if you know that, you're done, or else you're gone. The gold color will have 5% tolerance. If it was silver, it is 10%. Clear? This is color coding there for bits and CET. So advanced mainstream is not there. Advanced engineering is not there. So our deflection galvanometer is there everywhere. And important thing, they can actually play with this even in advanced a bit. That's the whole thing about current electricity. So we have done a lot, almost 45 questions, 160 pages. So please make sure to go through the whole thing. The chapter is done. And I'm telling you from last 2 weeks to start. So I hope you have started solving and you're done with most of it. If you're not done, please take a deadline, finish off till next Tuesday, your 1 week time, finish your HCV booklet, whatever you're doing, finish off at least 2 materials thoroughly. I did also send you a sheet last time on all instruments and everything. I hope you have seen that. There are some 30 questions. That should take care of most of the stuff. So yeah. Great. So that is one. Next thing is ray optics. Now we are going a little off bit. So we have done electrostatics, Gauss law, capacitor, and current. That's a good chunk. After that, we are left with magnetism, EMI, and AC. That's another chunk, the second part of the entire electromagnetism. So we'll finish off ray optics, then we'll go there. And then we are left with waves and wave optics and modern physics. So yeah, we are fine. We are going fine. So ray optics is another good chapter. I'm sure most of you are done in your classes. Most of you are done. Right. So yeah. So anyway, we are going to still do from scratch, but if you already know bits and pieces, it will help. So first thing, chapter is a very good chapter. As long as you remember the formula and remember the process, the questions are straightforward. There is very little way you can twist this. Yeah, you can twist and do stuff as usual, but unlike mechanics, right? Your life is little easy here. One of the favorite chapter for medical students because there is a bunch of around 15 to 16 formulas you have to remember. So that's the thing. So geometrical or the ray optics, the second thing is called wave optics. So let's do this thing. So what does this do? It deals with the particle nature of light. Which explains phenomena like reflection, refraction, and formation of image. Next thing. Now there are a few properties here. In geometrical ray optics, we always assume the light rays travel in straight lines in homogeneous medium. Homogeneous medium meaning uniform medium. If the medium is not uniform, the light rays can actually bend, which we will see later on. So two light rays pass through each other without interfering. Two light rays pass through each other without any interference. Light rays do interact in some special cases. We will deal that in another chapter called wave optics. Law of reflection and law of refraction. So these things are also the phenomena which we have observed. Like then there's one important thing called Fermat's principle. This is an important one. So what this principle says, right? A light ray, when it goes from one point to another point, it will always choose a path with the least time. A ray always chooses a path with the least time. If you're sending it from A to B, whether through a reflection or a refraction, you can be sure it will take a path where the time is minimum. And if it takes two different paths and reaches there, that means that both the things must have taken same time. This is also called as path difference, optical path. We'll see again that is later on. So these are the main assumptions there. So a ray will always choose a path with the least time, right? Light rays will travel in straight lines and homogeneous medium. They'll always pass through each other without interference and stuff. The first thing. So let's say we have a mirror. So let's say we have a point A here and we have a point B here. Now, if you send a light ray from A to the mirror, and after reflection, the light ray will come to B. So the question is, how should this light ray travel? Now we know from principle of reflection, theta1 is equal to theta2, but we need to prove it. So this is C. So let's say the light ray hits a point somewhere at randomly point C. Let this be theta1 and let this be theta2. Let this height be h1. Let this height be h2, which is constant, and this distance here, let this be x, and let this distance be d minus x, where d is the distance between them, or L minus x. So let the light ray, now C is some random point on the mirror. It could be anywhere. It could have hit anywhere on the mirror, right? Yeah, that's a Fermat principle. So that is the thing that we don't have a proof for that. So let the light ray go from A to mirror to B. So we are assuming it is hitting some random point C. Now see, the light ray could have gone like this also. The light ray could have gone like this. The light ray could have gone like this. There are infinite ways the light ray could have gone from A to the mirror to the B. Here C is the speed of light. L is some constant. So that's the distance between the 2 points. A and B are fixed. H1, H2 are also constant. So time taken to go from A to C to B would be the distance AC by speed of light plus distance CB by speed of light. So this would be root over x square plus h2 square by C plus root over h1 square plus L minus x whole square by C. So this is the time taken to go from A to C. And now you're saying from Fermat principle. So Fermat principle is like, there's no proof for that. So that we know by experiment or whatever, dt by dx must be equal to 0 for a minimum. So differentiate this. So this would be 1 by 2 root x square plus ht square. And then it's a chain rule. So that would be 2x plus 1 by 2c root over h1 square by L minus x whole square. This will be 2 into L minus x, and that's a minus 1 equal to 0. This will be x by root over x square plus h2 square is equal to L minus x by root over h1 square by L minus x whole square. Now, from here, if you look at the triangles, you can clearly see this is sine theta 1 and that is sine theta 2. Theta 1 is equal to theta 2. Clear with this? Yeah, you can prove with geometry, but I just wanted to show you with this Fermat principle. So the law of reflection, right? You can actually prove it with this. Are you clear with this? It will be useful. So later on, we can use the same technique to find even Snell's law also. Mu1 sine theta 1 is equal to mu2 sine theta 2. Maximum minima. So there we just used calculus to prove this. All clear with this? So law of reflection is not some random thing. It can be proved. So more importantly, that is one good thing. Matlab, it's a pretty good question if you are in 11th standard and when I'm teaching you calculus for the first time. Maximum minima. This would be a good question to do. Any doubts on the proof there? Again, really not that important, but I just wanted to show you see how they can manipulate stuff. So yeah, God, don't mix up things, Ray Arya. This is ray optics. So what is law of reflection? You can do multiple things. So we got a mirror. This is your incident light ray. Let's call it I cap. This is R cap. This is your reflected ray ka unit vector. This is your N cap, which is your unit normal vector. Angle of incidence and angle of reflection. The first thing, angle of incidence is equal to angle of reflection. Straightforward, learned in school. Second thing, the incident ray, reflected ray, and the normal are on the same side of the mirror and in same plane. Now, if you remember this, if three vectors are in the same plane, what are they called? They're called coplanar vectors. And what is the condition for coplanarity? Anyone remembers? The box product is 0. I cap, R cap, N cap. The box product, which is I cross R cap dot N cap. This is called box product. In case you forgot about this, we did this thing in the starting basic math and vectors. We did this thing here, the box product. So this was a condition. If the box product is 0, then we say the vectors are planar, coplanar. They're at the same plane. Page 197, in case you forgot about box product. Third, this is the most important thing. Relation between the reflected ray, incident ray, and the normal. If I give you vectors, how do you get them? So R cap is given by I cap minus 2 times I cap dot N cap into N cap. This is the relation between the reflected ray, incident ray, and the normal vector. Meaning in the exam, they'll say I cap is 2i plus j by root 5. They'll say normal vector is I minus j by root 2. Find the reflected ray vector. If it is in a plane, it is fine. If it's 3D, you will die if you don't know this thing. We derived this also in vectors. But let's do it again. So this we proved in vectors. Page 169, but I think we can do it again. You guys want to try? I'll give you a minute. Let's try to prove this. It will help you in the exam. Most people don't remember that. Can you prove that relation? All are unit vectors. I cap, R cap, N cap is given. Find the relation between them. Mm. So this was the mirror. I cap, R cap, and this is N cap. This was theta, and this was theta. Okay. Now what we will do, push that I cap forward. So the picture will become like this. This would be R cap. This would be I cap. So I join the two vectors tail to tail. This angle was theta. This angle would be 90 minus theta. And this angle would be 90 minus theta. So if you look at this height here, that is 1 sine 90 minus theta. So this height would be cos theta and cos theta. Of course, those are unit vectors. That means if I draw this will be R cap. This will be I cap. And this black one, magnitude, is 2 cos theta. And it is parallel to N cap. So this is 2 cos theta N cap. Then using the triangle of vectors, so I cap will be 2 cos theta plus N cap is equal to R cap. A plus B bar is equal to C bar. Now here, if you look at these two vectors, the angle between two vectors is defined when they're joined tail to tail. So if I push this vector I cap forward, this is how you get the angle between them. And this angle is 180 minus theta. So I cap dot N cap is mod I cap, mod N cap, and the angle between them cos 180 minus theta, which is minus cos theta. Take this guy and substitute here. So this will be R cap is equal to I cap plus 2 cos theta, that you can write as I cap dot N cap into N cap. Very useful when they're giving vectors in 3-dimensional, I plus J plus K and all that stuff. It's very difficult to figure out what is the normal, what is everything. It'll be quite useful here. Clear with this? There. Ray optics and vectors. So that's how you prove that, and that's quite an important relation if they give you. All clear how we got this? You should definitely derive on your own once more, because there's a good chance you will forget the formula. Then at least you should know that you can derive it pretty fast. If you derive it once or twice on your own, right, you will remember it. Any doubt so far? So there, I just taught you the principle of reflection. Let's see if you have questions on this. We got a parabolic mirror. Y is equal to x square. We have done this in foundation. No, we did this in calculus actually, I guess. So we got a parabolic mirror. That's your x-axis and y-axis, and this is your origin. You sent a light ray parallel to the x-axis. After hitting the mirror, this thing bounces off at an angle like this. This angle 120 degrees. This does not happen everywhere. Depending on where you are hitting, the angle can be like this, the angle can be like this, the angle will change. This happens at a particular point P. Find the coordinates of P. Let's get this everyone. We got a parabolic mirror, y is equal to x square. The light ray comes horizontally, hits the mirror and goes off at 120. Find the coordinates of point P. P.2. So 3 by 2. I'm not sure, Aditi. Yeah, that looks right. That looks right. Aditi, you got something else completely. Arya, I don't know what you even got. Okay, we changed it to root 3 by 2 now. Okay, maybe. That looks still wrong though. Another 30, 40 seconds. Let's get this. Yeah, right, Aditi. Yeah, let's see how to do this thing. Right over here. So the main idea here is if you draw a normal, so this green line here is your normal. And if you draw a tangent, this one is your tangent. We know this is 60 degrees. This will be 30 degrees because the angle between tangent and normal. So slope of the tangent is tan 30. But we also know the slope is nothing but dy by dx. Tan 30 is 1 by root 3 and dy by dx is nothing but 2x. Substitute as x is equal to 2 root 3 and y is equal to 1 by 12. Make sense? A little differentiation and then this thing. So the main idea was to use, the principle of reflection to find the slope, and once you got the slope, you can use calculus and finish it off. Clear? Now I can give you any other angle. I can give you 90 degrees, 60, whatever. You can handle this. Any doubts on this? Clear, everyone? How we approached it? Any doubts? Kashyap, clear with this? Yeah. Srihari? Tanishka? Clear? Next one. We have a spherical mirror of radius r. This is your principal axis you studied in school, so I'm hoping you know this. Even if you don't know, don't worry. It is just the thing which is passing through the center there. This was your center. Because it's a spherical mirror, there is a center C. You sent a light ray parallel to the principal axis. After hitting the mirror, it bounces and goes off like this. Let this point be X. And this is angle theta. And this is point A. So CA line makes an angle theta with the horizontal. And this point here is your P, which is pole. Find Px. So CP is principal axis. Don't say R by 2. Solve. You're not in 10th standard. Use entire parallel light ray parallel to the principal axis. It hits at a point A, which makes an angle theta with the CA line makes angle theta with the principal axis. After hitting the thing, it passes through the principal axis at point X. Find Px. That looks right. I think it is something is missing, Srihari. Okay, let's see. It's more of a geometry there. Don't say R by 2, huh? That's school ka stuff. That's a very special case. So if you just carefully draw this, you will notice if this is theta because alternate angles. And if that is theta, this is I, this is also theta because I is equal to this thing. So now if you make a triangle, C, X, and A, this angle was theta. This angle was theta. This angle would be 180 minus 2 theta. And C to A, it is a radius basically, because from the center, if you join any point on the circle, you get a radius. We can use sine rule here. So Cx by sine theta is equal to the radius, which is R by sine 180 minus theta. 180 minus 2 theta. 180 minus 2 theta is sine 2 theta, which is 2 sine theta cos theta. So that would be R by 2 cos theta. So Px is nothing but Cp minus Cx. Cp is nothing but radius, and this is R by 2 cos theta. That's your answer. Now, if theta tends to 0, right, then your cos theta becomes 1, and your Px ka value will tend towards R by 2. This is what you studied in school. So that means if you send the light rays very close to the principal axis, right? So let me show you that in the next page. So this is how it would look. This is what we'll be studying in ray optics. We'll always use this approximation. So if your light rays are very close to the principal axis, so if your theta is tending to 0, this is how the light rays will be. Then you can approximate, they meet all at the same point here. Something like this. So we are talking about something like this. So this is height h and this is radius r. The value h is much, much less than r. Example, if your radius is 10 centimeter, We are talking H is 1 millimeter. That's the kind of numbers we are looking at. These rays are called paraxial rays. Rays very close to principal axis. So our entire ray optics का formulas are derived under this assumption the rays are paraxial rays. And then we can assume the rays meet at the focus and we'll say that is focus and everything. So then your px will tend towards r by 2 and this is what we call as focus. So be careful. This thing, right, is valid only when your theta is small. If theta is large, don't say r by 2. Clear with this, everyone? A bit of a geometry there. So what we learned in school was that when the rays are very close, you can approximately say they meet all and meet at the focus. So in reality, parallel rays for a spherical mirror do not meet at the focus. So you always get an error if you use a big spherical mirror. All clear with this? Next one. We have two plane mirrors. 30 degrees. Let's call this M1 and let's call this M2. You send a ray parallel to M1. Find the angle of deviation. What is angle of deviation? The angle between the initial ray and the final ray. After all reflections, the ray which comes out or the ray which does not reflect anymore, that is the final ray. Find angle of deviation, delta. So basically delta is the angle between initial and the final ray. Tail to tail, huh? They just behave like vectors. This is a good one. It's like not tough and not really easy, right, Aditi? You just have to be careful with that. Right, Samya? Another 30 seconds. I'll show you. And this is something, if you remember, I taught you this in foundation, whoever are there, like when you did in that in 10th standard. Yeah. Nee, Advai. Na. No. Arya is another god. He gets the answer, but he still writes the wrong one and comes. Others, everyone else is wrong. You are doing a big fundamental mistake there. This is what you guys are doing. Like this, like this, like this, nah? That's what you're doing. How do you know it is going like that? Look at this picture. You will see something. If you actually draw the angles, you will notice that won't happen. This is 30 degrees. So this is parallel. This is your normal perpendicular to it. If this is normal, this is 30 degrees. If this is 30, this is 60 degrees, geometry. So the angle of incidence is 60. So it will bounce at 60 degrees. So if it bounces at 60, this also will be 60. This will be 30. Now ask yourself, this angle here should be how much? 120. Does 120 look like this? 120 is obtuse. So how should it look like? This is actually going like this. This is 60, this is 30, and this is 120. The light ray is actually going back to the mirror inside. It's going to bounce inside now. It's going to bounce inside. Now I'll draw the picture again. That is 30 degrees. So now you're bouncing at 120 degrees. If that is 120, then this angle will be 30. If this is 30, when you bounce inside, this will be 30. If that is 30, this should be 60. If this is 60, this should be 90. Making sense? That light ray hits the mirror perpendicularly. And what happens when a light ray hits the mirror perpendicularly? This is a very important statement, and we use this a lot later on in some really good problems. If a light ray hits a mirror along the normal, that is perpendicular to the mirror, it will go back the same way. It retraces the path. This is called principle of reversibility. It's also like, so if a light ray hits a mirror along the normal, quite a useful thing. Huh? Remember this. Later on we will use this. There are some good advanced questions also based on this one concept. It retraces the path. Means it will go back the same way it came. So if I draw the final path, this is how the whole picture will look like. So light ray comes, hits the mirror, then it goes and hits the mirror perpendicularly. I'll draw in green, so it will come back the same way. It will again hit the mirror here, then again it goes way. This angle is 180 degrees. And how many reflections happened? This is reflection 1, reflection 2, reflection 3, reflection 4, reflection 5. There are 5 reflections. All clear with this? Now, there's something more here. If that angle was less than 30 degrees, this light ray will just keep bouncing inside. It will never come out. You can ask a question like that. Find the angle so that the light ray will just keep going, bouncing inside. Because this is 90, right? If it is again less than 90, it will make an angle like this. It will bounce again. It will bounce. It will bounce. The light ray will get stuck inside. You can play like that. Clear with the question? Just have to draw the picture carefully. It's a good one there. Yeah.
Sir, how will we know that if the angle is less than 30 degree, it is
You
not going to
extend it, na?
go normally at
Try
some
Karona.
nth reflection?
You will see that angle keeps becoming smaller and smaller. Just try next one more time and see. For example, see when it hits here, if instead of 90, if let's say you got some 80 or something, and next time if you get something like 75 or something, that's clearly telling you that the angle is just decreasing.
Okay, got it.
तो एक और बार एक्सटेंड करके चेक करना पड़ेगा वो. Next one. This is another. This is an XY plane mirror. But in the previous question, this statement is important. It doesn't matter. Let the light ray pass through 10 lenses and 10 mirrors and hits the last mirror perpendicularly. It will just come back the same way again. This is a mirror in YZ plane mirror. Someone sent a light ray to Y plus 3J plus 4K. It hits this mirror, it hits this mirror, and it comes off. Find the final light ray. Find the vector of the final light ray. This is an easy one. See. So the main idea is this. It's like, perfectly elastic collision, oblique collision. So whenever a light ray hits this thing, there are two components, right? This is the component perpendicular to the mirror, and this is the component parallel to the mirror. So once you hit the mirror, you can clearly see only the perpendicular component will reverse, and the other parallel component will remain same. So you can say component along the normal will reverse. That's the whole idea there. The other components won't get affected. So for a XY plane mirror, what is the normal? Z axis. For YZ plane mirror, X axis. So this light ray here will be Z axis, right? So this will be 2I plus 3J. Only Z will reverse, minus 4K. Here only X will reverse. So minus 2I plus 3J minus 4K. Got this? So whichever mirror you hit, just keep reversing that particular perpendicular thing and you're done. But if the mirrors are not at angles or something, yeah, then you have to use that formula. That would be a mess, but yeah. Easy stuff. Hope that was clear. Great. We got a mirror and we got a screen. Someone shines a laser light. Yeah, so this was alpha, this is alpha. So this laser goes and hits on the screen, and this is point A. So A is the laser spot on the screen. The distance between this point here and this is D, that is given. The laser is always hitting there only. So you have some kind of a laser there. This is the scenario at T is equal to 0. Now what you did, you started rotating the mirror with omega. That means the picture will become like this. After some time, your mirror will become like this. After then, it is like this. So mirror is rotating. So if you rotate the mirror, the spot A will change. Find the velocity of A at this instant. So find the velocity at t is equal to 0, meaning at this instant, the moment you started rotating the mirror, yeah, I can ask you at any time t, but yeah, you can get this. Find the velocity, yeah, at time t. Hope the question was clear. Circular motion, reflection. A little of kinematics there. E cos square theta plus omega t. How? Okay, let's see. I'm not sure about the answer. Okay. Now, before jumping into the problem, there is one more standard result. If you know, this will help you. And there have been questions on this also. You're going to use this later on even for curved mirrors. Listen to this idea here. So if you have a plane mirror, this is your R cap, this is your I cap. Right? And let's say this angle was I and this was I. Now, if you rotate the mirror by an angle theta, remember the incident ray will remain same, but your normal vector also will rotate by theta. The mirror will rotate by theta. The normal vector becomes like this. Your incident ray still remains the same. You're not changing the incident ray. That means now the angle between these two has become I plus theta. That means the reflected ray will also make I plus theta. So initially angle between I cap and R cap was 2I, meaning I should take tail to tail, but yeah. So angle between them, so I'll just write between them is 2I. Now the angle between them is 2I plus theta. So what happened? The angle increased by 2 theta. So whenever you rotate the mirror by theta, the reflected ray will rotate by 2 theta. That's a standard result. So angle rotated by reflected ray is 2 theta when mirror rotates by theta. Remember this thing. This will be useful later on for prisms and lenses. Mirrors, we will do this. That means coming back to our question. So whenever the mirror rotates by theta, this line here will rotate by 2 omega, isn't it? That's the meaning of it. So I don't need to know everything else. So if this was your screen, this was the mirror. So let the mirror be however it wants. So it must be hitting like this. Initially, the mirror used to be like this. So the mirror rotated by how much? The mirror rotated by theta. How much was this angle? That was initially 90 minus alpha. And this is rotating with 2 omega. This was point A. No, that's not 90 minus alpha. How much was that angle? This was alpha, and this angle is increasing by 2 theta, right? The incident ray doesn't change, but this thing will change. So if mirror rotates by theta, this angle becomes how much? 2 alpha plus 2 theta. This mirror also rotated by theta. I need this angle. Let this be beta. This was the normal. I think I'm making this unnecessarily complicated, but I'm not sure. Like, this is alpha plus theta. This is alpha plus theta. Great. So that full angle must be alpha plus theta plus beta plus theta must be 90 degrees. I'm interested in beta, which is 90 minus alpha minus 2 theta. Theta is nothing but omega time. Great. And this guy is rotating with 2 omega. Yeah. And then this height will be y. And this distance is d. I need to do all that because tan beta is equal to y by d. So y is equal to d tan beta. If I differentiate this dy by dt, that becomes your velocity at A. This will be d sec square beta, then d beta by dt. This becomes velocity of A, and this is d sec square beta, which I can calculate the time, and d beta by dt would be how much? Minus 2 d theta by dt, which is minus 2 d omega sec square beta. And then you can substitute that. Sec square beta would be 1 by cos square, so that will be sine square alpha plus 2 theta, and theta is omega t. Yeah, and the minus sign indicates that y is decreasing, so A is actually coming down. All clear with this? Yeah, it's become mathematically more complex, but I hope you got it. So it's all about little geometry there. Any doubts on this? And the angles could have been better. Any doubts on this? It's all differentiation and geometry there. Great. Take a break. Come back by 9:45. We'll continue from here. Any doubts so far? Okay, come back by 9:45. The next one. Top view. So we got a mirror here. The width of the mirror is 2D. You're standing somewhere here. The distance between these two is D. This height is also D. And here, somewhere at a little far away, there is a road. And this road ka distance is also D. So on this road, we have a particle which is going on a straight line with speed u. So the particle is moving along this line with speed u. And what you're doing, you're looking into the mirror, okay? You must have seen this, right? When you're taking a turn in your society or something, they have these big mirrors. You actually look into the mirror when you're taking a turn so that vehicle from the other side, is it coming or not? So something like this, but this was a plane mirror. So this is going straight. The particle doesn't care what you're doing. It is coming from very far and it is going away to the far, and you're looking into the mirror. So you will see the image of this mirror. So for how long does this person see the image of the particle? So he won't see the particle forever. There is a limit of time. For how long does the observer see the image of the particle? Hope the question was clear. Right, Samyak. Let's try others. Hmm, Nee, Harshita. So what is the idea here? Look at this thing. You go reverse. If you send the light rays from the man, they will hit this corner and it'll go this way. And the light rays will hit this corner and it'll go this way. That means when the object is between these two light rays, so every light ray between this will reach him. This is also called as field of view. So basically the extreme case is when the light rays hit the edge of the mirror and reach the person. So that is your extreme cases. This is called as field of view. You must have observed it when you're sitting in an auto, right? In a certain position, you can see the driver in the mirror. If you shift somewhere, you can't see the driver. It doesn't mean the driver vanished. You're not in the field of view. So it's again little geometry there. So you always go the reverse. You send the light rays from the man, and then from there you try to figure out. So this ray will hit here. Let's call this point A, and it would go like this. This would be somewhere A dash. We can clearly see this angle is 45, and this angle is 45. If this is 45 and this is 3D, so this distance will be 3D. When the light ray hits this corner, let's call this is B, and it passes like this. This is B dash. So let's take this point as D. So A dash D was 3D. What about this guy? This angle, if I take it as theta, this angle will be theta. You can clearly see tan theta is 1 by 3. Because that is theta, the tan theta is 3. So this angle here, this would be your theta, and that is D. So this distance is D by 3. So this distance was D by 3. This distance was 3D. So this angle between the light rays, this is called as field of view. So when the object comes between these two light rays, you'll be able to see. This is one important concept. So the image will always form in the mirror. It doesn't mean you'll be able to see. It depends on where is the observer. Observer has to be in a certain position to see the image. So I hope those angles are able to figure out from geometry. So time taken will be A dash B dash by U. A dash B dash will be 3D minus D by 3. 8D by 3U. All clear with this? Right over here. Do have a look at this. Clear? Next thing. Now, this is important, okay? Theoretically, so listen carefully there. What is an object and what is an image? Point object and point image. So we define the point object point from where light rays emerge. So if the light rays are actually coming from a point, it's called a real object. Or appear to emerge. Or it gives you a feeling they're coming from there. But when you actually try to go and touch there, there's nothing there. This is called a virtual object. I'll give you some examples. What is a point image? A point where the light rays converge. This is called real image or appear to converge. Virtual image. So how do you find an image? So to find the location of an image, this is in general. So you put a lens, you put an mirror or whatever. Assume two light rays from the object. Right? And after all reflections and refractions, let there be 10 mirrors and 5 lenses and everything. It doesn't matter. After all reflections, I will simply say one thing. We'll go one at a time. So after refractions, reflection or refraction, they are the only two phenomena we have. Everything is a subset of these two. The point where they meet or appear to meet is the image. That's how you look at an image every time. So listen to this example. This should make things clear. Imagine we have a lens and we have a mirror. And let's say we have an object here. I'm just taking a case here. So the light rays will go through the lens. They will converge. They'll meet somewhere here. Let this point be I1. After going from here, let this light rays continue going forward. They'll continue going forward. They don't care. After this, the light rays will bounce off this mirror. Now, these light rays are not meeting, but when you extend them, the person outside will feel as if they're coming from I2. That's what he will think. So it gives you an illusion as if the light rays are coming from I2. These light rays will again pass through the lens. We'll change the color. And let's say they converge again. Let this be I3 and then they're gone. So that is when the question ends. So if they ask you find the position of the final image, you have to do all this stuff, right? Now listen to this carefully. So if you ask the lens, boss, who is your object? The lens will say, okay, my object is O, and it is real because the light rays are coming from there. Then you ask, okay, who is your image? It will say, so these two light rays from object went through the lens and they met at I1. And are they real? Yes, they're actually meeting. So this is also real. So lens will say, O is my object and I1 is my image. Great. Then you ask the mirror. Now see, the mirror does not know who is lens. If you ask the mirror, mirror, who is your object? Mirror will say, light rays are coming from I1. So my object is I1. Is it real? Yes, it is real because light rays are actually coming from there. And you ask, okay, what is your image? This will say I2, that is where it appears to coming from. And this is not real. Nothing exists actually at that position. It is virtual. And when the light rays go back again, then again you ask the lens. Lens, where are you getting the light rays from? Now it will say, I'm getting it from I2. And is this a real one? It will say, no, it is not real. It feels they're coming from there, but in reality, there's nothing there. This is a virtual object. And then what is your image? It will say the letters are meeting at I3. This is your real image. You're getting this. What is an object for one can become an image for something else. So how do you know whether something is an object or image? It depends on the frame of reference. Who is looking at I1? Is the lens looking at I1? Then it is an image. If mirror is looking at I1, it is an object. So what is image for one system becomes an object for another system. Are you getting this concept of object and image? This idea is important because next time when we solve this problem, when you solve for the lens, you ignore the mirror. And then when you solve for the mirror, ignore the lens. You do one at a time. That's the whole thing. So basically, this is like three independent problems. You do for lens, you do for mirror, then you do for lens again. When you're doing for lens, the mirror doesn't care. When you do for mirror, lens doesn't care. Is this clear, everyone? So few statements here. So what is object and what is image? It depends on the observer. So there is nothing rigid like this is always an object or this is always an image. So concept of the object depends on the observer. Who is looking at it? And when you solve this, the calculations are independent of each other. Means when you're solving things for the lens, you don't worry about the mirror. That's what makes, ray optics pretty good in that sense. They don't interfere with each other. Calculations are done independently for lens and mirror. This is a very important idea, everyone. This is the first thing you should be very clear. What's an object and what is a mirror? And this is how we will handle everything. This is what I was saying. You should know your formula and you should know your conventions. Chapter is straightforward after that. Any doubts on this page? Next thing, for a plane mirror, how does an image form? This you studied in school. Image in a plane mirror. So if you have a plane mirror and if you have an object, this is your eye. If you draw this line, this is M and this is your eye. So OM will be equal to OI and the line OMI is perpendicular to the mirror. So if you join the line object and image, it will be perpendicular to the mirror. When you keep something in front of a mirror, there is a lateral inversion. So B becomes like this. So here front and back gets reversed, not left and right. So when you stand in front of a mirror, what you're looking, right? You're not looking at your back. Your image and object are facing each other, isn't it? You're not looking like this. You're looking, what is back for you is the front for that. Front and back are reversed. Clear with this? Let's see a question. We got a mirror here, 45 degrees. We have an arrow like this. A, B, C, D, E. Draw its image. So this is the object. Draw the image of that arrow A, B, C, D, E. All these are 45-degree mirrors. Let's call this thing M1, M2, M3, and M4. And you have an object like this, an arrow. So this object will form a reflection. This reflection will create an image here. This image will be an object for this mirror. This reflection will form one more reflection here. So there'll be 4 reflections. Draw the images. Draw the images in M1, M2, M3, and M4. Meaning exam options will be like this, everyone. That will be one option. This will be second option. There'll be fourth option. They'll give you 4 options and you have to mark the right one. How will the images form in that 4 mirrors? Let's get this. Yeah. Hmm. Okay. C. What if it is not 45? Let's start from there. 45 is a special case. So if this was theta, look at the idea here. The idea was the the image and the object, right? When you extend them, they will always look at this point here. So when you're looking at this A, think about it. This distance here and this distance should be equal here. They're always from similar triangles, isn't it? If you look at image A, it will form A dash here. This also should be theta. So they will form congruent triangles. That means the image should form in such a way, from this point, you take in theta. So the mirror will become an angle bisector between the object and the image. So the arrow would be like this. It might not be perfectly right, but yeah. This is how it looks. If this is A, this is A. This is B, C, D, and E. You can B is the closest point here. So this is B, this is C, this is D, and this is C. So if the mirror is not at 45, this is how it looks. If theta is 45, it becomes vertical. It's 90 degrees. Clear with this? So theta is a better one. And what about this guy? So one thing we got it. So whenever you have 90 degrees, the image will always rotate by 90 degrees there. So this is how it becomes. So look at this question here. So we're going to use this result which we got. So whenever you keep a 45-degree mirror, the image will rotate by 90 degrees. Okay, listen to this carefully. This was the object grid. So image should rotate 90 degrees. So it will rotate 90 degrees. So the question is, where is the head? Simple thing. Which is closer to the mirror? The head is closer to the mirror or tail is closer to the mirror? Head is closer to the mirror. So this is the object. Now, that green one becomes the object here. So the green one is an object here. So again, you put a 45-degree mirror, this will rotate by 90 degrees. So it will be up. Head is closer, so arrow becomes up. Now this black one becomes an object. Again, what is closer? The tail is closer, so it becomes like this. So this is the object. So it becomes like this. So the final answer is left, up, right, and up. Got the answer? So every time it rotates 90, 90, 90, the only question you need to ask, who is closer, the head or the tail? And then respectively put the arrow ka thing. I hope that was easy. Making sense? Any doubts on this? This is a very bad periscope. Normally periscope you make only with two. Let's see one more. The next one is a good one. Let's say what a mirror. The mirror is going with V at an angle alpha. So this is constant. So mirror is moving at an angle. Someone projected a particle with U and theta and gravity G is there. So it's a projectile motion. So particle has gravity. Mirror is going with constant speed. Velocity, find the velocity of the image in the ground frame at time t. So we got an object projected with u theta g, projectile motion. There's a mirror which is going with speed v at an angle alpha with constant speed. Find the velocity of the image with respect to the ground at time t. Mm, right, Samak, you got the idea. So there's a small thing about this. Okay, let's see. So first thing, few things here. The mirror, you have to be careful there. Uh, but one thing I'll tell you, remember this. Whenever they say lens is moving, mirror is moving, stop it. Always do in the relative frame. Stop that mirror, stop that lens, and start the problem. Never try to do directly in the ground frame. It's very difficult. So whenever they say mirror is moving, object is moving, stop the mirror. Solve with respect to the mirror and get back to the ground frame. Use relative velocity. Lens is moving, same thing. It doesn't matter. Anything is moving, stop it first of all. That suddenly makes things easy. Now look at the problem with this mirror here. This mirror, if you look at the component here, it is actually going up with V sine alpha and it is going horizontally with V cos alpha. Now I said stop the mirror, but there is a catch. Look at this problem here. Let's say if you're standing in front of a mirror and this mirror is going up with V sine alpha, what do you think will happen to your image? Mirror is going parallel to itself, meaning think about it. Huh? You're sitting right, the wall in front of you is a mirror and the mirror is going to the left side. What will happen to your image? If it stays there, then it is science. But if the image starts moving, it's a horror movie. Just imagine the mirror in front of you, the image goes away and it is smiling at you like bye karke. That looks scary, right? Matlab, today you go to the washroom and then you look into the mirror and the image is looking at you and smiling. You really don't need a ghost to scare you. Like you can scare yourself. And then you get away from there, but your image doesn't want to move from there. It is looking at you like, what? Right. So this V sine alpha is not going to affect the image. The image will be always there. Doesn't matter how much this mirror goes front and back. So that's the main important thing there. You don't want that to move. It will be really scary. So V sine alpha does not affect the position of the image. So this is the first thing. Mirror ka velocity you have to stop, but that velocity is useless. That is the first thing. So we actually ignore this. So this problem is as good as the mirror moving with V cos alpha. And this is flying here. This is theta. And you know the components of this thing also. This will be u sine theta minus gt. This will be u cos theta, projectile motion, everyone. So solve with respect to the mirror. That's the main idea there, but ignore that component which is parallel to the mirror. Solve with respect to mirror and bring it back to ground frame. So this is how it would look. So if you stop the mirror, so you will think the mirror has come to rest. This guy with the vertical component will be u sine theta minus gt. And this velocity becomes u cos theta plus v cos alpha. That's what the mirror thinks about the object. So it will create an image exactly the same way, but in the opposite component, it will be u cos theta plus v cos alpha. And this will be u sine theta minus gt. But remember, this is the velocity with respect to the mirror. So velocity of the image with respect to the ground frame is velocity of the image with respect to the mirror plus velocity of the mirror with respect to the ground. Again, ignoring the v sine alpha. So that's completely ignored, like we don't care. This would be minus u cos theta plus v cos alpha I cap plus u sine theta minus gt j cap. That's your VIM. And velocity of the mirror is it's going to the left, so that's again another minus v cos alpha. Yeah, that's a little long, but you'll get it. So add them up. That's your answer. Minus u cos theta plus 2v cos alpha. Clear with this. So stop the mirror, solve, and then come back. All clear with this? Projectile and reflection and stuff. So let's do one more. We got a mirror at rest. This is making an angle theta. We have an object going this way, u minus I cap. This is your object. Find the velocity of the image, vector form, I cap, j cap. So we have a mirror at an angle theta, and this object is going with speed u parallel to negative x-axis. What will be the velocity? Speed will be u only. But what is the velocity vector? I cap, j cap. This is a good one. मतलब नहीं पा रहा हूँ. By chance अगर एग्जाम में क्लिक नहीं हुआ ना, क्या करना है? Simple thing. Put theta is equal to 90. Mirror becomes straight. The answer should be what? U I cap. You can guess. Let's solve anyway. Try. I'll give you a minute more. Okay, let's see. Right, Samyak. Right, Shaurya. See, the idea was this. Remember I told you? Imagine this way. If this object goes and hits the mirror, shouldn't the image also come and hit there only? That means, can I do something like this? So when this object is extend the object with this speed u. So if this was theta there, at the same time, your image is also traveling on a line. I told you just now, it will be a bisector theta. It is coming on this line. This is your image. So the object and image are coming to this line, making a theta. That means if you just look at the image, this is your image ka velocity u, and look at that angle. This is 2 theta. You're done, right? So velocity of the image will be minus u cos 2 theta I cap minus u sine 2 theta j cap. Make sense? So if this makes theta, the mirror will be a bisector. So that should be another theta. That means the angle is, this is 2 theta. And you're done. One step. And these are the kind of questions you'll get in mains and bits. All sure with this? There, that's a bit about it. So that's a little bit on reflections and stuff. I think we'll continue again in the next class. We'll do more on this, right? But this, if you see, we just touched the plane mirror. So next class, when we catch up, we will do few more on reflections, and then we will go with the spherical mirrors. So, okay, so that is the thing. So we'll wrap up with that for today. We'll finish off a little early. So, okay. So make sure to finish your current electricity backlog, whatever you have. Don't delay it anymore. It's a very important chapter, right? At least till next Tuesday, you have one more week time to finish it off. So start focusing on that, because after next week, you have to start reoptics. Okay. So with that, we'll wrap up for the day. So any doubts, anything else, please stay back and ask, or else you're free to leave. I'll see you guys again on Thursday, same time. We'll continue from here. So any doubts?